or the derivative that you have. Okay, so here what we have, just we substitute here instead of x by its initial value is 0, so here 0, 0, 0. Y, we don't have any term contain y, so the term here will be 8.5. So this is the value of the slope now. And the value of y at 0 is given, it's equal 1. Okay, the value y0 is 1, this one. And this is the value of the slope, 8.5. And this is the value of h. So now the new estimate y1 just equal this value. Okay, Shabab, so the first step is okay to find y1. So if you want to check here the true value and the true error, we have the value of y and we estimate the value at when x equal 0.5. So this is the true value when x equal 0.5, and this is the value when x equal 0.5 as well. So here using the numerical method, you can see we have the value or the estimation is 5.25, while the true value is 3.21875. Okay, and the error here you can see it is minus 63%. Okay, so to improve the estimation, we can use another step or second step. Second step, we have y2. So in our alteration, we have y2, that means y equal 1 or I equal 1. So in this case, we have the end alteration, we have y1, if x1, y1 multiplied by h. So we just substitute. Here y1 is given in the previous estimation, this y1. We already computed here. This is the value of y1, 5.25. So this is the value of y1. Okay, this is the value that we compute. After that, we substitute by the value of x1 and y1 in the equation that we have. This is the equation that we substitute to find the value of this loop. So this is the odd equation. So this odd equation at the beginning, just type it. This is f of x and y. So this is f of x and y. Okay, so this is f and x and y. After that, for all the solution, you will use this equation. So this is f x y. For different value of y and x, we try to estimate this slope. So here we just substitute in the odd equation, and this is the value of h. Don't forget this one, 0.5. So now the new estimation is 5.875. So the true solution when x equal 1, so here because at y2 we have x equal 1. If you remember here, we have at x2 the value of x is equal 1. Okay, we have here x equal 1. So here the true value or the exact solution when x equal 1 is 3, while the estimation is minus 95.8. Sometimes, yes, we will see later, even if we increase the number of alterations, sometimes the error sometimes will goes up because the solution here is near to each other, or we move around the solution. Okay, because here, but if you reduce the step size and instead to use 0.5, if you reduce step size less than this one, so in this case we can enhance the approximation. But later this it will goes down, but sometimes it goes up and then goes down depending on the estimation. As we said before, sometimes the function is contain curvature like this one, so this also it can cause some big values of errors. Okay, otherwise here or pendant like this one, so these values, maximum values or minimum values, these sometimes will be reduce the maximum error. Okay, or a big change in the value of the error. We expect to be this goes down, but sometimes it goes up. So, but after that, if we increase the steps, this will goes down later. So here, let's take this table. So this is the table that we have here. This is the table explain if we do all the steps. As we said, we need the steps from x equal 0 to x equal 4. Okay, so this is just complete the solution that you need. Here you can see when we have x, we already compute this initial value. When we have x1, this is our estimation. This is the error method, this column. Usually you try to do this like this one, or I gave you something like this one example. And this x1, x2, x3 like this one. So here we can see we have two types of error. We have here the global error or the global truncation error. And here we have the local truncation error. Okay, so the global truncation error is the error usually, the global, we take the difference between this one and this one, and we take percentage over the true, we'll get this error. The truncation error or the local truncation error, usually this from Taylor series. We'll see this in the coming slides. Usually this from Taylor series expansions. And usually the local error is due to the use of the Taylor series to compute the value at x I plus 1. Okay, while for example the global error just is based on our steps that we calculate. So for each step we can compute the value of the global error. So the global error is the normal error that we compute. The normal error, that means the true minus the estimation over the true. So if you take this one over this one, here for example, the first step we have here to find, for example, the second row, when x equal 0.5, you find the global error is equal minus 63.1. Okay, this is the global error. So this value, how we can compute it? We take the value here. We take this value over this value, or minus this one, the true minus the estimation, okay, over the true value, So this will give us 30 or 63.1. After that, to compute 95, so we take 3 here, the true value, minus the estimation over the true 3. So this will give us minus 95.8. Okay, so we do it for all the steps, we'll get it like this one. So we'll see here the error is fluctuated, increase, decrease, depended on how far or how the curve of the signals. Okay, and as we said, we can summary that. This problem you can see here, the error is increase, decrease, increase, decrease because of the value of the step size. Because sometimes we jump about above the solution, and after that we try to return them back. So in this case, the results not be accurate. But a good way is to have less steps or minimum step size. So in this case, we can minimize the value of the error. The truncation error or the local error is due to the truncated Taylor series. That means when we use Taylor series expansion to drive Taylor's error series, so we will use an error. What will be the remainder? What's the terms that we omit? So this we consider this as the local error. As usual, also we have errors due to round off. If we remember this one, so this is the type of the errors that we have. So this is the local error or local truncation error, or due to the approximation using Taylor series. If you remember, this is the functions using Taylor series. Okay, so in the Euler method, we take only these terms. Euler method, we consider only, or we take only these two terms, the first terms. So this is represent Euler method. So what is the truncation error? So all these terms that we omit here, or we ignore, this is considered as the truncation error. Okay, as the truncation error. So here also, to simplify, the second derivative of the function is dominated term for the truncation error here for the Euler method. Sometimes for simplify we use just the second order derivative, or dominated here for truncation error here. So the truncation error, or the approximation truncation error, again, if we know the function, so this will be easy. We can use the derivative of the function. If you don't know the function, so we can use the mean, and this will be approximation as well. Okay, so here the local error in Euler method, it is an order h square, and because the Euler method is the first order polynomial or first order equation, so it is global error will be in order HO. So in this case, we'll see that the true or the local error will reduce double than if we have the global error, and the local error will give us a good estimation of the error. Okay, so the local error you'll see in the table. If you return back to the table here, you can see here at the first step we have the error is minus 63 here, minus 63 here. We have almost half of the values here, because the error here is reduced by half or of order h square. Okay, so you can see it is decreased, but it is increased based on the function. But the reducing or the reduction that we can get on the location error, we can see it is because this is power h square. If we reduce the step size, that means instead we have 0.5, we reduce it to 0.25. So in this case, this error reduced over 4, for example. Okay, that means this error divided over 4. Here we start from 63, so here divided this over 4, what will be, you have the new result. Any question, Shabab?
Yes, Doctor. In the previous, in this example, no,
yes.
the previous one, sorry.
Yes.
We compute the slope. Why we didn't solve it as the previous one?
Where is one? In the example?
Yes, the example, I think, yes, 25. I think 25. We compute the slope in the first step.
25.
Yes, this one, Doctor, I think.
This is the last lecture. I did not consider it today. This I explained the last lecture. This one I explained today.
Yes, I mean this one. We compute the slope here.
Yes.
Why we didn't solve it directly like the previous question in the previous lecture?
How we solve it directly? You mean we apply integration only?
No, we substitute y0 and the formula. I get and I get the answer.
Yeah, this is the formula. You can substitute directly here. Here, this is the formula. A student here, they like it to type it like this one. يعني in the exam, you can type it like this. يعني you have here y1. Okay, يعني you can type it here y0 plus here. After that, just type the function that you have, because here you have h is 0.5, isn't it? This multiply by the slope. What's the slope? The slope is here, is given -2. Just type -2. You have here x power 3, like this one. Okay, here plus x square. Okay, this -20 x plus 80 or 8.5. So this is the solution that you have. This x is not multiplication. So this one. So here you have the value. You can apply like this one. No need to compute the slope individual and compute this one individually. You can do it directly. That you mean?
Yes, thank
you. Yeah. Do it directly. No need. Yani, this is just to show you the steps. Okay, just to show you the steps, but directly you can substitute. Usually the student do it like this one. Okay, so just you type here, you apply directly, one step to find the solution. It is easy for you. But the student, for example, may they make mistakes, so they can do it in clear steps to get partial grades or something. Any step. This is just we learn you here. After that, you can do it in one step. So do illustration like this one, what we did before. The last lecture, we do it in this form. Okay, this is y1, we do it like this one. y2, do it like this one, y3. So it is easy after that for you. Just you have the calculator. Just will change the first value. See that? So you can do it يعني 5 minutes to complete this one, alterations. Okay, so this يا شباب, what's the difference between the truncation error and the global error? The global truncation error, as we said, is the same thing as what we studied before. We call that the relative true error, or the relative percentage true error. This is the same thing, so we call this the global truncation error. The second type is the local error. The local error is the truncation error from the Tyrrell series. Okay, so we use this form to find it. We use this form to find it. So this is the graph represent the difference between the two methods, the exact solution, and we use the step size 0.5. So actually, if we use step size less than this one, so you'll get a better estimation. So this is the true estimation, and this is the estimation, and this is the true value or the true solution of the function. So how we can estimate the error, or estimate the error of the Tyrrell series or the error method? So if this is given the first order derivative, so in this case we need to use the second derivative of the function. So this is the complete error. As we said, this is the error that I will cut this one. So this is the error, the truncation error here. Okay, can you see? So this is the Taylor series expansion, and here we have, this is the error or the error method, and this is the error, the rest, we call this truncation. So if you want to take the complete local errors, so we'll take all the terms that we want from here to the end. So this will be the total error. So the total error, it's equal the first, second derivative, and third derivative plus the fourth derivative to the derivative power n that we have. Why we stop here? Because the first derivative is equal 0 for this one. Okay, because if we take the first derivative, or this is the second derivative of the function, this is the second derivative of the ODE. This is the second derivative of the ODE. That means it is the third derivative of the function. Okay, so this is the third derivative of the ODE. That means it is the fourth derivative of the function. You can see this one. If we add more derivatives, so the rest will be 0. So no need to add more terms. So we call this the total local truncation error. But if you use, we can combine them to get the error here. Combine them, we compute the error due to this term, compute the error due to the independent for the third derivative, compute the error for due to the fourth derivative. After that, we combine them. But for in sample way, we can use only the second derivative. We can use the second derivative to compute the value of this error. Any question, Shabab? So this is the graph represent when we reduce the step size as usual. If we reduce the step size, in this case, we can have a good accuracy. So this will enhance the accuracy. So we can see this is the true value. This is the example that we did. And this is the new estimation when H is half, H2 is equal half H1. So in this case, we can see we reduced the error here. So here I want to show you examples using MATLAB from some websites. I think you can, I will zoom this one. So we can implement the function here, define the function. This is the definition of the function. Function, any name you can use it, Euler method. This is derivative. After that, you can define the function here in the command window. dv or dy dt, just the function. T-span, just the interval that you have. Okay, so here we have, and this is y0, it's the value of y or the initial value of y. Here is the step size h. So all these 4 points are the input for this for the system. We have only one output. This is y, or 2 outputs is y and t. So next step, we can determine the span. So t0 at the first point, we have here the final point of the span or the interval at t final. And then we divided this interval using the step size. How many steps that we need? Okay, so this is the t. It starts from t equals 0 increase step size until TF. This is the final value. If you want to guarantee that the final value is TF, so in this case, we need to use this condition. So after that, this is the length of n, or of n based on the length of t. This is the initial value of y, zeros. We start with y equals zeros. We use the same size of t. After that, we define the first iteration, t equal 1. And then we take the iteration from I equal 1 to n minus 1 because we already defined one of them. And this will be the Taylor series expansion. So Taylor series is at xi plus 1, it's equal, oh sorry, yi plus 1 equal yi over the derivative of the function over the span. So the previous span, so this is just h here. So after that, here in the common window, we can determine or type the function that we have. Any function you define. So this is the function, just you save it in your computer. After that, any function, just type it here. Define the new function. So any function, you can solve it. So the new function that we, this is 5 multiplied by exponential minus 5t minus 0.5y. Okay, so here the initial value y is equal to 3. T0 starts from 0, and the final, or this is the interval. Okay, the interval that we have, T0, 0, and TF is 10. The step size is 0.5. You can do it the same, but with different step size. And after that, we do it and we plot it using, we apply this function to solve this function here. This is the solution here, approximation, what we have. So this is the true value, the blue one. And this the red one with dots represent the Euler estimation. Okay, so if we try this one with minimum step size, we can get a better estimation. So as we said at the beginning, one of the major problems of the Euler series or the Euler method, it's that we start the interval if we have like this one. So this is the interval from this point to this point. So we take the one slope from this point. If this graph like this one, we take slope from the beginning of the intervals and we consider this over the whole interval. So in this case, we can see we have here huge error. So the method that's developed to enhance this one, instead to have a single estimation, so we can have some points here between. One of these methods, we call this the midpoint method. The midpoint method, we use here an estimation. We estimate the midpoint, we compute the slope at the beginning. After that, we compute the slope at the midpoint to correct the slope and the estimation of our, instead to have the estimation at this point, so we can correct the estimation at this point. And then we can take another midpoint like this one. So for each step, we compute the midpoint between the 2 points like this. This depended on the number or the step size that we have. So we can compute different midpoints. Depending on the alteration that we do. And the second method, we call this Hyones method. And Hyones method, usually we do it in 2 steps. The first step, by using Euler method like usual, Euler method to estimate the slope. The second step, we use trapezoidal rule to integrate these functions. Okay, if you remember trapezoidal rule, it's integrated numerical integration rule. It's used to integrate the function. So we can use trapezoidal rule here to correct the protection, our protection that we have. So that means if we go with highest order method, we can enhance the accuracy and also reduce the error. So here, high order methods also can be derived using Taylor series. And example of this one, for example, if we take the second order polynomial. But the problem with these methods, the high order derivative, it's more complicated. Although the high order series or Taylor series methods are more accurate than the Euler method, the high order Taylor series more accurate than the Euler method. But the problem, as we said, if you want to compute the second and the third or the high order derivative, we need to do this by using analytical solution, and which may not be easy to find. Okay, because here we need to find, for example, the second derivative analytically for this ODE equation, and the third derivative by using analytical solution. And sometimes this is not easy to compute. So this highest order that we'll study Yohn's method, and this is midpoint. Okay, sorry. Okay, so this improvement that we said because of the fundamental source of the error in the Euler series is that the derivative at the beginning of the intervals is assumed to be applied across the entire interval. Okay, so to modify this one, we can use two steps. And these steps we call these Runge-Kutta methods. All these steps we call them Runge-Kutta steps, single step or multiple steps. So Yohn's method, it's one method to improve the estimation of the slope of two derivatives for the interval, one at the initial point and one at the other of the point, at the endpoint that we estimate. And after that, these two derivatives, we take the average of them by using trapezoid rule. We have first derivative at the beginning and one at the end. After that, these two derivatives, we take average of them to obtain an improved estimate of the slope for the entire interval. So this is the Yohn's method. As you can see here, this method, it can be used to give a better or to provide better estimation of the derivative. So instead to compute the slope at this point, one step at the entire interval. So here we can use two steps. So the first one, we call this protector method. Protector method is not just Euler method. We have here Euler method. So we use this one, protector step, to calculate the slope at xi plus 1. So after that, we take these two slopes. We already have the slope now at xi and xi plus 1. This is the slope at xi plus 1, the new one using the protector. And the slope at xi, this is the initial value. We start with the initial value because this is the previous one. This value of y, the estimate of y here, we use it to find the value of the new slope. Also with xi plus 1. After that, we take the average between them. The average with the initial value, for example, if we talk about y1, so this I will be 0 and here will be 0. So here the slope at initial value, and this is the slope at xi or x1, and here at y1. We take the average of them and multiply by h to get a better estimation. If you look for this one, this is represent trapezoidal method. As you remember, trapezoid method, it's equal f at b plus f at a over 2 multiplied by b minus a, and this is the same thing as that we have. So now we use the integration method to integrate this ODE equation to correct the steps. We call this the correction steps. So this is graphs represent how this is work. So here we start with the slope at the initial value or the beginning or at xi. So this is the slope that we draw at xi. And then we use Euler method to find the slope at the endpoint. Now we want to draw also slope at this point. Okay, so we have slope at this point and slope at this point like this. At the endpoint like this. So now we have this slope at this point and the first slope at the beginning and at the end. If we average them, so we can finalize with more accurate estimation. So this will be the new estimation that we have. So this is the average of the two slopes. So this is the beginning. This is the Euler method. You can see the Euler method is too far. This is the Euler method represent. This is the Euler method. It goes far from the curve, from the ODE or the solution or the exact solution. We start with the slope Euler method at the beginning, and then we use trapezoid rule to find the slope. Here, not trapezoid. We use also to find the slope at the endpoint, and then we use trapezoid rule to take the average between them. Okay, so we have one on this side and one on this side, so the average between them will be this one. And this you can see it is more accurate the two estimation because it is on the exact solution. So now what we use here in the Huygens method is by using Euler method, trapezoid rule to find best estimation. This Huygens method, we can do it in different techniques. Sometimes we do, it is based, we can say it is based in protector corrector method. So we have protector and corrector method. Here, how many correctors, how many protectors that we need, we can determine this in the question. The question will clarify this one. So the corrector steps can be used more than once to provide better estimation. So we can do predictor here. After that, I start iterate the correctors. So until we falls below a tolerance, a certain value of the error. Sometimes we ask you to do this one protector, one corrector only, one protector, one corrector. So in this case, you do one protector, one corrector. And sometimes we ask you to do protector and alterate the corrector. So now these values, you alterate the corrector only. You do one protector and you alterate the corrector. After that, you reach certain error, and then you will start a new protector. And then we'll alterate the corrector like this one. The examples, inshallah, will be clear when you go to the examples. So this method, ya shabab, this is provide good accuracy if we compare this with the Euler method. So here, the accuracy here of Huygens method, it's an order 2. That means OH square. Also, it can obtain the exact results when the solution y is quadratic. If we have quadratic polynomial, also this it can help to provide a good accuracy and a good solution. So here it has the error of order h square. If we compare this with the Euler method, in the Euler method we have the global error in power h. And the local truncation error here in Huygens method, power h power 3 or O h power 3 cubic. While in the Euler method we have h power 2. So that means this method, it can help to enhance the accuracy. Okay, so this is the method that we talk about. We have here, this is the protector, this one. We do it the first slope. After that, we compute the slope at the end, and then we can find this is the corrector just to correct between them. Okay, to find a solution at this point. We take the average between them. Okay. So this is one example, Shabab. We have here an example. Use Hyone's method to solve the ODE equation. This is the ODE equation, and we have here, this is the initial condition. Here the question, sometimes we specify the solution here. Use only one correction step. So in this case, you need to use one correction step. No need to alterate the correction step. Sometimes we ask you to do two correction steps. Sometimes we alterate the correction step until we reach certain value. Okay, so this is the question like this one. And the question here, it's asked to determine the value at y.1 and y.2. That means x equal 0.1 and x equal 0.2. Okay, so, okay, time up. Okay, sorry.